last couple of years I've been giving talks about Disco in Erlang Factory, and I was with Nokia Research until last September, hacking Disco, and the guys are still there. And well, I left to found a new startup. The startup is called Bitdeli, and it's still related to data and like making data processing, especially real-time data processing, really easy. And basically the thing that I want to talk about today was the kind of the observation that I had to make when I left Nokia, and like we kind of, I mean, like the nice thing about startups is that like you get this awesome opportunity to start like doing things from scratch, which is always very awesome. I mean, that's always the best part, like 6 months of the company that actually you are just hacking intensively and like you have no limitations, and like, well, of course, after that you realize that like, well, the kind of the hard parts start after that. But anyway, so I started hacking Bitdeli with my co-founder 6 months ago, and the idea was to build the kind of this like a scalable platform for processing data. And I will talk more about Bitdeli later, but the basic challenge that we faced compared to especially kind of to the previous situation that I had with Disco at Nokia Research was the fact that, well, Nokia Research has this like very nice big petabyte scale cluster running Disco. And like if you happen to have infrastructure like that available, and like if you have it like your own data center and your own servers, I mean, things are quite well. I mean, it's very easy to kind of build systems having that infrastructure in mind. But now, given that like we are a small bootstrapping startup with no like not like millions on bank account, so basically what we had to start thinking is that, okay, so definitely of course we want to leverage like the public clouds like Amazon and Rackspace and so forth. But if we just take the old mindset and like just let's say that okay, so we take like 100 nodes from Amazon Cloud and keep them running 24 hours a day, and then we did the math and we found out that that's absolutely kind of beyond our budget. So we had to come up with a different idea, and we kind of started by thinking that, okay, so what are those things that like one has to think about when actually kind of starting to build a system from scratch for the cloud today. And really kind of this is the question that like you see often with existing systems, let it be Disco or React or MongoDB or whatever system, and like people send an email to the mailing list asking that, okay, so how do I run these systems using Amazon? And like the funny thing is that, well, I mean, you could like in the best case, I guess what would happen is that, well, I mean, you do exactly the same as you have been always doing. You just like launch instances and you have Linux servers and you set up the machines and so forth. But of course, in practice, what you see people answering and what people have noticed is that it's actually quite different environment. So especially when it comes to I/O, when it comes to like the stability of the instances and then various other things. I mean, actually, you can't just do things in the same way. So basically, the question that then like we like asked ourselves when we started building Bitdeli was this: that okay, so kind of turning the question upside down, so that like given that like we want to use one of these clouds, well, I mean, we have no other option. We can't afford like having our dedicated machines, dedicated petabyte scale cluster from day one. How should I build my system? So knowing all these issues that kind of the cloud has, and especially knowing that, okay, so we want to handle big data. Of course, the kind of the constraints are a bit different if you are, let's say, you are building like a messaging application, and like then, well, I mean, it might not be about big data and so forth, but I mean, it's a different set of constraints. But I mean, today I will be talking about especially kind of a cloud, like with respect to kind of a building really data-intensive systems. I don't know. I mean, many of the lessons might be applicable to other things as well, and really. Kind of what we noticed is that there is this like environmental pressure like for doing things in a different way. So I mean, if this is kind of the old way of doing things, I mean you have like a certain environmental pressure. There's like things are changing, the environment is changing. So basically, what you need to do is that you need to evolve. You have to do things differently. So basically, kind of what I want to kind of talk today is like. Actually, four like a main observation, four like main constraints that we set to ourselves in the beginning. Then I will like talk shortly about like how we actually realized those constraints and how it ended up being in the end. And of course, like, well, I mean, it goes without saying since I'm here that actually the whole backend is written in Erlang. And I will mention like a couple of good reasons, at least in our point of view, why I still think after like having the system now in production, you can go to bitdeli.com. It's a live system. You can actually sign up for free, and hopefully the site is alive, so that it actually, I think that's really a good way of building systems for the cloud. But let me start with the four observations that we made. So the first one is maybe maybe quite obvious. So, well, I mean, maybe the part, not the part about like having short-living instances, but the fact that, well, I mean, like the nice opportunity that you get with the cloud is that you can actually launch instances really fast, so you can as well have many of them. And there are a couple of reasons for this. So, well, I mean, the first obvious reason is that, well, I mean, the instances may end up being short-living even if you don't want that to be the case. So, I mean, like, this is what the Amazon EC2 promises. Well, I mean, it might look good on the paper that, well, I mean, you have like quite a many 9s there and then 1 5, but actually if you do the math, it like ends up being like 20 minutes downtime per month per region. And that's like one good thing to notice, that it's not per instance, but it's per region. So basically it means that like if you are running instances in like, let's say the kind of the Oregon data center in Amazon, it might be that actually, I mean, like the region may be down for 20 minutes and like still they are kind of within their SLA, the service level agreement. So, I mean, that's something that like, well, I mean, we're thinking that, of course, we want to build robust system as anyone else. We are providing a platform, so it has to be robust. So knowing that there is the kind of the issue with the downtime, I mean, we have to kind of take this into account right from the beginning. So that's one good reason for why we thought that, okay, so we want to kind of take this approach that instead of having something that we think that it's like live and up, I mean, every instance is up and live like 24 hours, like, and like have like 9 nines availability, whatever. I mean, we take the approach that actually any single instance can go down. Another interesting observation related to these small instances is the fact that, of course, well, I mean, like if you have ever dealt with infrastructure and data centers, you know that maintaining the illusion of stability is, of course, very expensive. So, I mean, we know that in practice there are many reasons why servers go down. And of course, like if you are an infrastructure provider like AWS or Rackspace and so forth, you guys know that that's of course like really an expensive part of the business to kind of have people on call and like kind of switching disks and whatever it takes to kind of keep the systems up and running. So the interesting thing that like what Amazon provides like nowadays is that they provide this thing called spot pricing. So actually what the thing shows, what the graph shows here is the kind of the last month and the price per hour per instance, and like then like three different like pricing models that they provide. So the kind of the topmost line here, which is something like, I guess like it's 38 cents per hour, is the on-demand instances. The next line here are reserved instances. So if you are kind of ready to make an upfront payment of a couple of $100, you can of course get like a cheaper per hour price. So that's cheaper. But the cheapest price by far is actually for spot instances, meaning that basically you are bidding for the amount of money that you are ready to pay for the instance to stay up. And like for most of the time, the price is pretty stable, but occasionally there is a spike. Maybe somebody kind of is bidding more than you are, or maybe the machines are going down, so they have fewer resources available. And that's basically why there are these spikes. Well, now the thing is that like if you want to minimize your cost, like basically you are kind of trying to bid the lowest amount or a little bit above the lowest amount, like looking at the historical average maybe. And then of course what happens here is that like since you are not like bidding, your bid is not high enough, your machines die. I mean like basically Amazon reserves the right to kill your instance without any prior notice, which is of course, now if you imagine that like you run some like classic system which doesn't handle this like sudden crashes like very gracefully, of course that's really bad. But on the other hand, like if you take that as one design criteria, then like things can get pretty interesting in pricing point of view. So this is something that I find very, very interesting nowadays, that actually there's this like a very interesting direct connection between the pricing and the kind of basically the price per hour for running your system and the actual architecture. So it's not so that like there's this, you have architects like just designing the system and then it's very hard to see that, okay, so what's the kind of the long-term kind of a cost effect of certain design decisions. But nowadays actually there can be very direct correspondence between the kind of the design of your system and the price you end up paying for running it. So that's just pretty interesting. Another kind of interesting point about like having many small instances is the fact that let's say that like you want to get some amount of resources. So let's say that like you know that like you want to get like 17 gigs of RAM. So what do you do? So of course you can actually go to Amazon and like you can get like one high memory instance that ends up costing something like almost like $400 a month, and that's how you get 17 gigs. And of course like now many of you think that okay, that's like an outrageous price for 17 gigs, so you can just like get a dedicated machine and that's all good and fine and much cheaper. And of course, that's the case. But where it gets really interesting is that if, again, I mean, there are many considerations to be taken into account, but if you can actually kind of instead take 29 micro instances that cost, well, I mean, a little bit more, but I mean, still on the aggregate level, you have many more resources available. I mean, you get the 17 gigs, a little bit more even than that. And now you have, instead of having one fragile instance, you have 29 instances running. And well, I mean, then the thing is that depending what you want to do, you might actually want to take like 10 small or 3 large and so forth. And that's kind of interesting that you really have this a different workload, different server types available. But really the interesting fact is that actually kind of having many more instances, 29 instances versus 1 instance, actually doesn't make a big difference in price. But of course, in the architecture point of view, again, it makes a big difference, a huge difference. So, well, I mean, the next point, the next kind of observation that we made, if you look at the React mailing list or well, I guess not so many people have been running Disco in Amazon, but basically any system that people have been running, especially kind of NoSQL systems that people try to run in Amazon, usually the first thing that people complain about is the unreliability of disk access and the kind of random latencies that you see and all that stuff. So, I mean, well, given that we are not in control of the infrastructure, it's of course hard to kind of fix those issues per se. So we decided to kind of start thinking that, okay, so how would our system look like if instead of using Disco IO, we would totally avoid using it. And now, of course, if you have ever used AWS, you know that there are several different options for using local disk. You have really the local disk, it's a physical disk on the box. But it's of course very unpredictable. I mean, it can go down at any point. I mean, disks crash and so forth. And well, I mean, there are strange features that due to the lazy initialization and formatting that they perform, actually it benefits from being initialized, and that kind of complicates things and so forth. Then Amazon provides something that they call Elastic Block Store, which is basically a network attached storage, which kind of supposedly fixes the reliability issue because, well, I mean, it's supposedly more reliable. But the fact that it's actually attached to, it's actually network attached storage, and it's a multi-tenant system. Many people are using it at the same time. It's very unpredictable when it comes to a single volume. So what people end up doing often, and if you actually, there are many good benchmarks about this, and if you want really good performance, what you have to do is to take many volumes and then have something like RAID over the volumes, which basically means that given that the cost is of course per volume, and the more volumes you have, the more you end up paying. So I mean, that's oftentimes very expensive, and again, of course, that adds complexity because now suddenly you have this like a software RAID running in your stack as well. And really kind of the thing that's really kind of annoying in the end is that even though, I mean, it would be really nice to think that, okay, so something like EBS actually provides you really good robustness, that you don't have to care about disks crashing. Of course, things like this happen. So this is actually an actual email that I got. Luckily, we didn't lose any data because of that. But I mean, given that you bought this service and you thought that, okay, so now I'm using some awesome a SAN device that never crashes, it's not nice to get this email that just casually mentions that, well, I mean, there happened to be a disk crash and we lost all your data and there's nothing we can do, and good luck with your next volume. So. But yeah, that happens. So basically, if you want to avoid losing any data, especially if you want to avoid losing any customer data, you might want to consider different approaches. So third constraint that we thought is that, well, I mean, like I mentioned already before, there are many different instance types and the prices are actually interestingly nonlinear. So it really makes sense to actually separate different workloads. So basically what I mean is that now if you consider typical application, it doesn't have to be data-driven application per se, but any other application as well, basically you have different types of things that it needs to do. So I mean, typical application nowadays has of course a web front end, meaning the Nginx or Apache server that you are running on some server somewhere. And that's of course something that handles some decent amount of data. Let's assume that you are not doing crazy caching on that. But I mean, of course you need some amount of RAM and resources to kind of handle the incoming data. The latency requirements are, of course, pretty strict, since, of course, you want your service to be really responsive. So, I mean, when somebody loads your front page, it needs to respond in basically just tens of milliseconds. And, of course, given that, of course, you are creating a popular service, you can get thousands of requests per second. And of course, like what's really important is that, like, of course, if you have this like a one web front end and it fails, and like suddenly your site becomes totally unavailable, that's of course totally horrible, and that's the last thing that you want to happen. Of course, in practice, you want to have like many failovers and so forth, but that's really kind of, you don't want to kind of crash ever the web front end. So that's one layer, that's one type of workload. Then interestingly, in many applications, you have this kind of a second layer, which is still low latency. Like, I mean, we want to kind of give results in less than a couple of hundred of milliseconds, basically meaning anything that like should respond to a single HTTP request. Now, if you think of a popular service like GitHub, for instance, so, and they have these like visualizations where you can go to your repository and see like who has been forking it and so forth. I imagine that this could fall into that category. Of course, they might be cached most of the time, but in practice, I mean, if you have to generate something like that visualization on the fly, you want it to be done in a couple of hundreds of milliseconds. Not quite as fast as loading a single resource over HTTP, but still it should be pretty fast, so people don't have to wait for a long time. And again, I mean, that's not like, you are probably not dealing with huge amounts of data. And like in that case, like failing that, well, I mean, like you can have like redundancy. I mean, given that it's a backend service totally, I mean, it's kind of easier to handle. And in many cases, like one feature failing on your website is not as bad as the whole website failing. So, I mean, that's not quite as bad. Then, like, especially in data-driven applications, of course, there's the whole layer of actually doing the big data crunching and like taking all the data that you have received and like doing some awesome stuff for it. So like MapReduce definitely falls into that category. And then, of course, basically the amount of data that you handle can be unlimited. In our case, well, I mean, our service happens to be such that most likely we won't be handling more than like 1 terabyte per one customer, say. But still, I mean, the kind of basically it could be anything. But in that case, of course, the latency isn't an issue. That's pretty much the definition of batch processing, that nobody's waiting there. And like, I mean, people go to have coffee when they are running their MapReduce shop and so forth. So it's not so sensitive to latency, which is, of course, kind of totally, again, like affects the design. And again, I mean, of course, like most likely you are not like running many of batch requests per second. So at least not of that scale. But then like an interesting fact is that given that like you are crunching a lot of data and like, and like you have potentially you are kind of consuming CPU resources and so forth, that might actually end up costing a lot of money, and like, I mean like resource-wise. So it just like simply needs a lot of resources. And then there is the kind of the interesting last tier, which is the fact that, well, given that like if your service is made of those like 3 main components, then of course you have the kind of the system running. So I mean, oftentimes what you want to do is that like you have this kind of like a testing or a best effort tier, basically that you can use to kind of test things and so forth on the background, given that there are any available resources. But if some customer happens to be doing something, then of course you don't want to steal the resources from them. So that's the best effort layer. And now, of course, this is like very much dependent on your application, how you want to map these to different instance types. But like, for instance, like one interesting observation what we made with our service is that, well, I mean, we have like definitely like low latency requirements on the backend side, so we have to perform certain operations in less than 500 milliseconds, but the operations that tend to be really spiky. So I mean, like basically you kind of run like some piece of code for a small amount of data, but I mean, really, it doesn't last for more than a couple of hundreds of milliseconds, which actually happens to be a good match for the micro instance that Amazon is providing for a really cheap price, because this is something that, like, of course, like not many people can actually guarantee on their like a design of their system that actually the load will be really spiky. But again, that's the point, that if you are designing your system from scratch, and if you can actually take into account right from the beginning that actually, well, they are providing these instances that actually make it very affordable to run spiky workloads. Well, I mean, what if we actually design it so that we can really separate those spiky workloads and like take advantage of the fact that you can do it in an affordable way? And then, like in the same way, I mean, like in batch processing, well, I mean, if you are really like ready to trade the latency to kind of the money that you end up paying, again, I mean, you can actually maybe deal with like not huge cluster instances that cost like a lot of money, but actually maybe some smaller instances. So that's like really important in cost perspective, that actually you really can design your system hand in hand with the fact that, okay, so what kind of resources, what kind of infrastructure like there is available, and it also taking the cost into account. Now right. So this is like actually, well, I mean, this is like an interesting thing that like I noticed when we started, of course, like it was like very much common knowledge that actually something like AWS is actually kind of can end up being pretty pricey, and like especially looking at like single instances and so forth. Then of course we did the math, many different versions, and like many different scenarios. But I mean, just like looking at like, for instance, like at this basic question that like if you want a single instance with 1 GB of RAM, so what do you do? So basically, I mean, these are like just a few popular providers. I'm sure that like you can find one like a hosting provider that like provides you 1 gig of RAM for less than like $31 per month. But I mean, these happen to be the popular choices, and of course there are other considerations. You might not want to go to the most obscure provider in the end of the day. And like basically the interesting fact about this is that like especially for the past year or so that Amazon has been pushing the prices down, and they have been introducing new like layers of pricing, like different layers of like reserved instances and so forth. It might actually end up being so that if you design your system carefully, actually it might be a very cost-efficient solution in the end of the day as well. And of course, well, I mean, you should do your math, and like of course, like amount of RAM is only one consideration, but it can be cost-effective. So now actually this is my like favorite point, and this like very much like ties into Erlang. So of course the kind of the main point of like building a system like this, well, I mean, like let's say that like if you are a research environment, maybe what you want to do is to just focus on like the massive scale of data crunching. But given that like if you are providing a service to your customers, really the most important thing that like you want to provide is high availability or robustness of the system. So you absolutely don't want it to crash. And that's of course like why people like Erlang, so that's a very nice language for doing that. And that makes life very interesting in like cloud point of view, where like as I showed before, I mean, many things can crash and many things can go wrong. So now a very interesting question in like system design point of view is that like given this like very fragile and very heterogeneous environment, how do you actually design your system so that it's super robust? And actually an interesting concept that goes beyond like robustness is this concept of anti-fragility. And basically it's something that I stole from this like famous author who wrote the book about Black Swan and so forth. And he defines the kind of the anti-fragility by saying that, well, I mean, it's something that actually it's not only robust in its environment, but it's actually something that's like designed to be mishandled and designed to be handled carelessly. So that's kind of a very nice definition for a system that runs in the cloud, where we know that actually kind of like the cloud provider can be really mean and kill your instance at any point. So basically, your system is not only robust, but it's something that like actively copes against hostile environment. And this is of course like nice connections to the kind of the biological systems that kind of very much operate in the same way. And well, this is like I mean, there are like many ways to approach this question, but like one way of looking at this is like a very operational. So now thinking that like you have a system already operational and you are running something, and let's say that you are running it on a dedicated machine. And now let's say that like instead of just like machine crashing and like there is a hardware failure and like the machine totally dies, so well, that's kind of an easy case. But I mean, like kind of a nastier case is that what oftentimes happens in more complex systems is that actually the system doesn't crash per se, but it just like becomes more sluggish and like slow and like somehow doesn't like work quite as it should and so forth. So another question is, what do you do? So, well, I mean, if you are running like things on dedicated machines, and like let's assume that there might be some, let's assume that the problem is not in your software per se, but it's some like environmental issue, like something is going wrong on the switch level, or let's say that like somebody actually you have like kind of like a backbone in your switch and somebody kind of cut the connection or something like that, so that it kind of doesn't work quite as it should. So basically kind of if you happen to be lucky enough that actually you don't have to fix the machine by yourself, you call the data center and there's like some guy with remote hands and like tries to do something. But I mean, in the worst case, especially if it's weekend, I mean, it might take days depending on your support contract. So, and it's very manual process and like not very nice, especially if your environment is very fragile. Now, if you are running a virtual server, let's say that you are using Linode or like many other like a standard like a virtual server providers. Again, I mean, if you have this issue, I mean, most of the time it's actually due to the fact that like it's a multi-tenant system and somebody else is on the same physical box doing something crazy and like eating up your resources, and that's why let's say that the disk I/O is sluggish. So again, I mean, you call the support and say that, well, I mean, my instance is acting funnily, and like then they will move your instance maybe on the fly to another box, and like in the best case that can be done in hours. But again, now, well, that's of course something that it takes resources, and it's not nice, especially when you happen to have many instances running. But the interesting fact about the cloud is that given that it's so fast to kind of launch new instances, you can take a totally different approach, which is that instead of like trying to fix the problem, you just accept the fact. And like you see, I mean, like let's say that you are using Erlang, and like you have this nice concurrent heartbeat process that checks the machine and checks the like different like health factors in the system, and notices that, okay, something is going wrong. So what do you do? Well, I mean, you just kill the instance. So, I mean, you do the same thing that the provider would do, and is that like, well, I mean, you can do it automatically, that like you just get rid of the instance. And you can be extremely opportunistic that you just launch a new instance on another box, and like if you don't happen to be lucky, it might be, of course, something that's region-wide, and I mean, doesn't fix the issue, and you might be even clever enough to try a different region. But the thing is that, like, in the end of the day, most likely, eventually, the kind of the situation gets fixed, and like the kind of you didn't have to do anything manually. And that's like a very interesting change in the mindset that like you can actually build your system so that it's self-healing to a degree. Just as an artifact of the fact that like if you consider it right from the start that actually the whole environment is hostile, well, then you can treat the environment as hostile. So whatever bad happens, you just kind of kill it. And that kind of course, like really kind of plays nicely with this idea of crash-oriented programming, which is like very well known in the Erlang space. So next, let me just quickly go through the kind of the actual architecture that we ended up using, I mean, based on these observations. So, I mean, just quickly before I go to details, so, well, actually, that should say Bitdeli there in the middle. So, like how our system works is that, like, you can actually send events either from your web application or the backend or wherever you like, simple JSON messages to our REST endpoint. We receive the events. We have this layer that scales nicely, can take thousands of events per second. And like what's really kind of nice about our service is that you can actually write a script in Python that we keep running in the cloud again, that takes your data like in real time and does some processing, maybe something simple like a simple format conversion or something more complicated like, let's say, like even like sentiment analysis using, let's say, natural language toolkit for Python. And then it like produces the outputs that then you can access over another API and then get access to the JSON results. So basically what it means is that like you want to build a custom dashboard for your internal analytics, or you want to build a let's say some like a fancy solution for tracking sentiments of what people are saying about you in Twitter. I mean, this is really the easiest way to do it. But I mean, like as you can imagine, of course, we have a couple of issues here. So we have to make sure that like in every possible situation we can receive the events. Whatever happens to the machines, we can keep running the scripts that the user has provided. Also taking into account that it can be arbitrary Python code, so it can do anything crazy. I mean, eat like as much memory as there happens to be on the instance, and anything can happen. And also, of course, that we want to make sure that like if you create, like if you put your visualization on the front page of New York Times, we can serve it. So there are like interesting architecture questions. And so this is pretty much the kind of the architecture. So it's quite simple. So the kind of the thing is that like we have the kind of the coordinator process in the middle, which is like written in Erlang, and then we have this like small processes, and like, well, I mean, there are not exactly 3 of them, but many of them, and it really depends. I mean, everything is very dynamic, and that kind of ties back to what I mentioned about having many small instances. So instead of having like kind of dedicated server to do this thing and dedicated server to do that, it actually the kind of the coordinator guy here basically kind of launches every possible instance only on demand. So if the instance goes down, it notices it and like it launches a new instance. So in a way, it treats the Amazon cloud almost as like one big Erlang VM, that where the kind of things are linked, so that like these are almost like individual Erlang processes, but actually in this case they happen to be individual instances in the cloud. So if anything goes down, it just like launches a new one, or if there's more demand for certain resources, it just like launches more instances. And of course, that's exactly what the kind of clouds were made for. So if you are just using them as a simple hosting provider, I mean, well, that's not the best way. But really, the nice thing is that you can do things in this way nowadays. The second thing about like the disk I/O was really something that we wanted to avoid. And well, I mean, of course, the kind of if you want to persist something, in the end of the day, you want to put the stuff somewhere. And like, well, I mean, Amazon happens to provide S3, the simple storage service, which is an interesting abstraction, gives you interesting notion of persistent storage, but of course it's only eventually consistent, and there are many tricky things about that too. But I mean, basically what we ended up doing is that we try to keep as much data in memory as possible. Of course, that's also something that like you need to be careful about when you know that like instances may go up and down at any minute. But then every now and then we flush the data to S3 in a custom structure that can be accessed easily. But this way we can like, to a high degree, we can avoid like using any local disk, which actually makes things like very, very nice. Since it's kind of funny thing that like using usually the network interface is much faster than using the local disk. So if you just keep, basically you have these small instances that basically act as buffers or caches for incoming or outgoing data, then well, I mean, you have just these like small caches, and then like you fetch data like on demand basis from S3. So then like the question about like the separate workloads. So well, I mean, like there are like different classes of instances, and actually there is the kind of the coordinator guy here in the middle takes care of scheduling. So there is a simple scheduler that like knows that, okay, so I mean now we need resources of this type, and like do we have any available resources or not, and if not, if there aren't enough resources, then it launches new ones and so forth. So of course an interesting question is that, well, I mean this is something that we really kind of also wanted to make sure that, well, the very annoying fact about the AWS, the Amazon cloud, is that actually you can't set a credit limit for yourself. So they just take your credit card number and then like, well, off you go. And then like if anything happens to go wrong in your code and like you end up launching like really many instances, and like you might like wake up next morning seeing that actually a bill runs in like thousands of dollars. So it's very annoying that they haven't fixed this issue, but of course it's an obvious that like probably they don't want to do it. So I mean, but you have to be careful about it. So I mean, like don't launch instances in an infinite loop or anything like that. Now, of course, the question about like the anti-fragility and robustness. Well, I mean, like if you look at the previous slide and like you see that, okay, well, I mean, it's a pretty kind of a typical thing. You have the coordinator process, the master process, and of course now you think that if the master goes down, everything goes down. But actually the beauty of this approach is that like actually all these machines are independent. So even if the coordinator process goes down, these guys continue doing their job quite as usual. So that's really nice about the fact that actually they have different physical boxes, even in different physical geographical regions, that actually they can really operate independently. And then of course eventually the coordinator comes back and notices the situation and like then fixes the thing. But I mean that's really part of the anti-fragility, that not only you can like kick out any of the single instances here, but you can even like kick away the big guy in the middle, and then still the kind of the thing keeps operating. And that makes the system really robust. So of course another thing is that, well, there is the simple storage service that's kind of like, I mean, like all the kind of the components access it. So of course we assume that that's something that like Amazon takes care of, like keeping running, and it's worked pretty well this far. But that's another, of course, assumption. So now, like that was the architecture and those were the observation. Now just like a couple of points like based on the kind of the recent experiences we had about Erlang when building the system. So by the way, how much I have time left? So just a couple of minutes. 12 minutes, okay, should be enough. So well, I mean, there are of course like many like answers that like why to use Erlang, and like actually, well, when I started to use Erlang, of course, the kind of the official answer and the kind of the thing that was everybody was saying is that Erlang is really awesome at building concurrent systems, and like if you want to do many things in parallel and then so forth, and you want to send messages back and forth, you should be using Erlang. Well, more and more, especially like due to the fact that like now there are many other languages like Golang from Google and then Scala, and well, even for Rust from Mozilla, and like many language closure that actually provide the same functionality. I mean, of course, well, I mean, probably many of us have been asking ourselves that, okay, so why am I using Erlang? So should I be using Scala, or should I be using Golang, or should I be using Clojure? And actually, well, so the answer is not so much that, well, I mean, you can do concurrent stuff with Erlang, but there are actually a couple of reasons why, again, I, like after building this system and after seeing how it works, I mean, I'm very convinced that actually Erlang is the way to go. And like really the first reason is simply the failure model. So the kind of the fact that actually if you look at the architecture here, it very much like fits the mindset here. And that's a feature that like, of course, you can most definitely simulate the same idea and the same fault model in different languages, but it just happens to be so very convenient that it's so much like built in the Erlang culture and the Erlang components that actually that's the way how you build systems. So that's definitely kind of one of the biggest reasons why I think that like Erlang is a good match for building systems for the cloud and for handling big data, which by definition almost nowadays means that actually you have to do like horizontal scaling and cope with the fact that like things go wrong and so forth. And the second thing, maybe even more importantly, is simplicity. And that's simply because of the fact that, of course, well, I mean, doing something like this would be, of course, very awesome, and especially having this like very biological, anti-fragile system that just doesn't go down ever is, of course, very nice if it was really easy to do. But of course, it's not easy to do. It's super hard. And like, at least I think that it's very hard to do complex things with complex tools. So I mean, like, really, that's really the reason why I think that Erlang is really kind of exceptional in the sense that you can do stuff like this with a simple language. And really, if you look at any other language in the same space, you really don't get the same level of simplicity to model complex problems. That's really great. So now some lessons learned. So I mean, that's actually something, like I mentioned, I mean, like each of the small boxes that you saw there are actually running Erlang VMs. When we were like working with Disco, and what Disco still does, the Disco MapReduce, is that it uses like distributed Erlang. In this case, well, I mean, the whole system is so kind of dynamic. Actually, kind of what we ended up doing is to actually use simple HTTP between different instances, and that actually kind of seems to work very well. Not only due to the fact that, well, I mean, it's easier maybe to handle like really large networks of these things, but also due to the fact that, well, we have noticed that like, I mean, like the Erlang virtual machine can crash, not due to the fact that Erlang might be buggy. I mean, that occasionally happens as well, but like really rarely. But even like more often due to the fact that actually there's something funny going on in the environment that like just kind of makes life very hard for the Erlang virtual machine. So one thing is that, well, I mean, this is of course not specific to Erlang, but any system that like basically on a single instance I mean, if you're running like the system on your local laptop, and especially on Linux, I mean, Linux has very nice like overcommit features, so you can just keep allocating memory as much as you like, and like things work. Or in the worst case, I mean, you start swapping and things get slow. But oftentimes in these like cloud environments, actually you have a hard limit for the amount of memory you can handle. So basically, if you try to allocate, if you malloc more than like certain amount of memory, then it just crashes. So we have seen that happening. Another thing is that like it's very easy to run out of like all kinds of resources, not only file descriptors, but like that's something that happens. And especially like, well, the fact is that like still the kind of the Erlang environment sits on the disk, and like anyway, I mean, like the disks are very unreliable. So if anything goes wrong, I mean, like the disk can hang, and like the latencies can be huge, and the whole system can get really unreliable. So it would be it is easy to kind of have this concept that even the in an individual Erlang virtual machine can crash. And of course, then when you are doing many things simultaneously on the same machine, it might be that it's just the other, like the rogue process that actually eats up the resources and like makes again life hard for the Erlang virtual machine. So that's like one thing. Well, this is more specific to doing like really like big data stuff and really heavily kind of a data-oriented stuff when you potentially handle like lots of stuff in your Erlang virtual machine. Well, it goes without saying that binaries are awesome. So I mean, it's a very nice way to kind of not just the fact that, well, you can do binaries, but actually the fact that you can actually use binaries in a pretty clever ways to pack your data if you happen to be very, very kind of memory intensive and you want to be efficient with that. Of course, that goes without saying that, well, that's of course an optimization that you should do only after you have noticed that that's actually an issue. But it's really nice that you have that tool at hand when you need it. And also, actually, another thing that I have learned to appreciate is the fact that, like, when you need it, actually, you can create like you can write a few like very tactical nifs. I don't think that the kind of the right approach is to kind of start creating like large portions of your system as a nif, even if it might seem as a performance bottleneck. But I mean, doing very small like library functions, I guess that's what nifs are for. And like basically offloading certain things that would be very hard to do in Erlang in an efficient way. You can just take an off-the-shelf, let's say some like a super efficient library from Google that does something, and you can package it as a nif and like wrap it in a chain server, and then like suddenly kind of many tricky let's say data structures become much simpler to implement. So this is just, I don't know, I mean, this might be something that like does not apply so much generally, but actually kind of one thing that we noticed that really helped in designing the system is that actually well, I mean, of course, like we have like a huge number of gen servers, as everybody does. But what also seemed to be a good idea is that like they are pretty independent. So we try to minimize. I mean, it kind of goes back to the kind of the whole mindset of having these many small instances, many small short-living instances. And now you know what happens if you have like this like many linked like gen server instances, and if one of them goes down, of course you have this like a domino effect, and that's exactly of course what should happen, and then many things can go down and so forth. And of course in the worst case, if you haven't like designed your system carefully, it might be that like in the end, like basically kind of when this like dominoes go down and down the path, I mean like eventually your whole system is down. So, and even if it comes up after some time, it would be nice to kind of have this like a circuit breakers in the middle to make sure that like basically kind of the things stay reasonably independent. Another kind of a very kind of a nice feature that we found out to be really helpful, especially with respect to hot code upgrades, is the fact that actually gen servers, when they launch and when they start, they actually can reconstruct their own state based on some, let's say that like some external resource like the simple storage service. So instead of us having to kind of somehow really carefully manage the state in a gen server, actually we can just kill the gen server, and like the gen server is capable of just like fetching its like whatever it happens to need for its state, and then it basically kind of can like become alive without any external help. So that's really super convenient, and that kind of saves you from the trouble of like writing functions to kind of port from one state to another state if you do hot code upgrades. So now let me kind of this is kind of a fun thing that I kind of wanted to kind of challenge you about. So I mean, it's kind of called Erlang Anti-Fragility Challenge. So you might know the Chaos Monkey if you have been reading the kind of the blog articles by Netflix, where they kind of introduced the idea of Chaos Monkey, this little process that actually kills like servers in your cluster like every now and then randomly, and you have to build your system so that it actually survives the Chaos Monkey doing its job. Actually, another interesting version of Chaos Monkey for Erlang, which I call Chaos Monkey on LSD, is the kind of this Chaos Monkey that actually goes to your like Erlang process and actually randomly corrupts the state of a random like gen server. And now an interesting question is that, well, I mean, we might like discuss like whether this happens in practice or not. Well, I think that it really well might happen. And the interesting question is that, of course, well, I mean, the gen server in question that happened to kind of be a victim of Chaos Monkey, I mean, like, of course, probably goes down eventually. But now the interesting question is that does your whole system like slowly disintegrate over time if this happens? So, I mean, like the typical example might be that you have this gen server that, let's say, handles like database connection. And now if the Chaos Monkey hits you and like corrupts your state, and like then, well, I mean, the state somehow kind of maps to the database that's persistent, and then like kind of the database gets corrupted, and then other processes are using the database, and like over time the whole system disintegrates and like falls apart. So that's of course something that you don't want to happen. So, but I mean, the question is that can you actually build your system so that even if this happens, and even if whatever happens, whatever random happens, and like the kind of you end up having like a corrupted gen server, your system somehow kind of might actually kind of have like some part that like doesn't work, or maybe one customer like is not able to access their data or something like that. But the idea would be that actually the whole system shouldn't go down, and really the kind of the effect shouldn't kind of percolate through the system, but it should like stay contained within a certain area. And it's kind of an interesting idea if you think about it and think like in terms of your service that like how does it actually react to a situation like this? So that's pretty much all I had to say today. So yeah, I'm happy to answer any questions. So thanks. Sure.
You should let the gen server to restart the state.
Yeah.
What do you use it to store the state?
Well, I mean, well, there are like a number of things. So basically, like in our case, the data ether came, so the state ether comes from the simple storage service that it actually kind of like the gen server knows that, okay, so I should be accessing this resource, and it goes to S3 and like gets whatever data it needs to get from there. Another case is that actually, let's say in the case of the coordinator there in the middle, it actually can access the Amazon APIs and ask that, okay, so kind of tell me the state of the environment and what instances are running, and then it kind of reconstructs its state based on that. So of course it depends on your environment where you get the data.
So did you build this kind of storage, or you use something already built?
So basically we are using the Amazon S3 as a storage backend. So. Well, I mean, basically, well, I mean, like there are like 2 of us working for Bitdeli, and like my co-founder is working on the other interesting problems that are on the client side, I mean, like JavaScript stuff, and I was like responsible for the backend, so it was like 6 months full-time work. So. 6.
2 people?
Yeah, 2 people. Yeah, but I mean, it's a startup, so I mean, like we're sitting in the garage hacking 24 hours. Yeah.
How do you handle data corruption? When your storage gets wrong, how do you handle this situation?
Yeah, well, of course, the thing is that, like, well, I mean, like, there are, of course, different ways to kind of, like, try to deal with corrupted data. But actually, what we do is that we don't deal with corrupted data per se. What we do is that we make sure that, like, the corrupted data stays as isolated as possible. So even, like, for a single customer, we want to make sure that even if there happens to be, like, a local corruption for data, I mean, like, we minimize the effect of that corruption. So we can access all data before and all data after that. But I mean, there might be some limited amount of data that's corrupted.
Do you use some kind of checksums or something like that?
Well, you could. Basically, we rely on like the S3 to kind of keep data somewhat like not corrupted. But I mean, like, yeah, you could be doing more. But really, what we wanted to do is to kind of isolate and like make the effect as minimal as possible, and not kind of make sure that like we can fix every possible corruption. Yeah.
So when you came up with this idea of chaos monkey on LSD, you
Yeah.
had a very specific example which triggered the thought about that. So can you tell us about that?
Yeah, so I mean, like, of course, well, I mean, you know, I mean, when you are building this like highly available systems, you kind of go through all possible things that can go wrong. Let me think that what was the specific. I mean, basically, in every kind of single component, we were considering that, like, I mean, like, especially when you kind of design your system with the idea in mind that like anything can like kind of fail at any possible time. So then, like, basically for every change server, you have to think that, okay, so let's say that like if this thing happens to die at this point, so and how would it actually affect other things? And I don't know if there was any kind of at least there wasn't any kind of a horrible incident like kind of a memory getting corrupted and the bits flipped. So, yeah.
What kind of algorithm are you using to actually schedule? So like in your architecture,
Yeah.
the central part, the control is really almost like a point of failure, right? If you run on the cloud, are you using a particular algorithm to optimize the allocation of resources? There seems to be a big one of the cost, right?
Yeah.
Optimize that stuff. And then the first question is also, have you thought about a more biological approach, where basically the individual nodes are talking to each other within the same resource cluster, so that the other goes down, they can actually themselves spawn some neighbors.
Oh yeah, yeah. Well, okay. So sorry. I mean, I should repeat the question. So what was the first question again? So I guess.
What kind of algorithm you
Oh, okay. So what kind of algorithm I'm using for scheduling? Yeah, that's a good question. So basically, it's a rather simple algorithm that actually, I mean, it's a modification of like a first in, first out, but like taking into account like a number of constraints. So there are some like locality constraints. So some things need to always run, or would be beneficial to run on the same box. And then the other thing is to kind of like taking into account the kind of resources that are available. So I don't know if your second question. So what was the second question again? Yeah.
The second question was more about, is it a point of failure?
Oh yeah, right. Yeah, well, I mean, it's okay. So let me go back to the kind of first question still. So I mean, like you kind of, it's very true what you said about the kind of that it's of course like a very kind of important in cost efficiency point of view, and that's also another thing. And especially it gets interesting when you do spot pricing. That actually, since I mean, like you saw the graph, and there are certain spikes. So of course, if you know that certain types of instances at certain point of time are very expensive, so of course your scheduler shouldn't start using those instances. So you should avoid doing that. So basically, we have this is of course somebody who has done who has been in the financial industry probably can come up with a really efficient algorithm for doing like really good spot pricing. But we have a pretty simple model that just like make sure that we don't like spend like huge amounts of money on like stupid things. But basically, that's also something that the scheduler takes account. And then like going back to your second question about is it single point of failure? Well, I mean, it's not single point of failure in the sense that like the whole thing can actually survive the kind of the machine going down. Actually, how it works currently is that like I mentioned in the other slide about like different workloads. So actually, our like web front end currently actually runs on Linode. So for the fact that actually, due to the kind of the resources that we need, I mean, it's cheaper to kind of keep it running there since it needs to be up 24 hours. And anyway, I mean, that's not the part that like we keep kind of taking up and down all the time. So basically, a couple of times it has happened that like the central process has gone down, and actually it doesn't affect the systems. I mean, kind of like within like I guess currently it's some like 12-hour period or so. So if there's somebody who can like fix the situation in 12 hours, then it's okay. I mean, like you could possibly increase that, but that seems to be working rather well. So. Yeah. Yeah.
Was that also a case where you couldn't use just Erlang calls? If so, what was the decision making?
Okay, so the question is that like why we are using HTTP, actually it's HTTPS and not like distributed Erlang. I guess that's the question. Well, I mean, we were using, and Disco is still, the Disco map produces using distributed Erlang, and it works rather well when your system is relatively stable, when you have like, let's say, you have your own dedicated boxes and so forth. But what we noticed is that like even in an environment like that, it can kind of get tricky at times, especially if you have anything kind of resembling network partitioning. I mean, timeouts happen, and like, I mean, it's kind of hard to rely on, let's say, something like just like monitoring the kind of the node monitor, so that like you can, like you basically assume that you would get a notification when a node goes down. So basically kind of we ended up using, and well, I mean, then there's the other issue, of course, is that, I don't know, I guess actually that might be fixed by now in the Erlang virtual machine, but at least it used to be so that, of course, the traffic between the nodes in distributed Erlang is not secure. So, I mean, it's just using plain TCP. And of course, that's an issue in a public cloud. So we wanted to use HTTPS. And it seemed easier than like trying to build something like distributed Erlang over SSL, which actually now might be working. I don't know, but that was like one consideration at the time.
Okay. I think if you have more questions, you can.
Yeah, thanks.